Good morning, everyone. My name is Rose Yu, and I'm an assistant professor at the computer science department in UC San Diego. So it's certainly a humbling experience to speak about fluid dynamics after Stephen. But because I'm in computer science and I come from a different perspective, so my research focused on developing machine learning methods for analyzing large-scale spatial temporal data. And fluid certainly is one example of such spatial temporal data. And here's a logo of our lab. And you can see that there's a rose in the logo, but hidden in the logo, there is a letter S and T, stands for spatial temporal. So we know that fluids can deeply influence our life, right? So it describes the evolution of complex phenomenon from weather patterns, from wildfire, even in ocean currents, and even our blood circulation. So the recent development in fluid mechanics has generated a huge amount of data, both in simulation and in real world. This opened up new opportunities for machine learning, which is the field that tries to extract insights from a huge amount of data. So in fluid dynamics, there's a lot of excitement these days. Well, one of them certainly is deep learning. So deep learning essentially has revolutionized the field of AI, right? As we can see here, this is a typical image, like picture of ImageNet, which is a classic benchmark in computer vision. And since 2012, the emergence of deep learning has significantly improved the classification performance on ImageNet. That was a huge breakthrough in machine learning. And similarly, AlphaGo was made possible because of deep learning, and it beats human professional players in the field of Go. And likely in the Google robotic farms, now robots can learn to open doors, pick up objects, where before robots are manually programmed through control algorithms. So naturally the question is, well, how about fluid mechanics or fluid dynamics, right? Can we use or develop new type of deep learning algorithms that can make impact in the fluid dynamics field? Well, if we think about fluid dynamics, the difference of this type of field compared with images or Go games is that there's underlying physical principles that governs the dynamics of this kind of data. So it is actually very important to develop deep learning algorithms that can understand physical laws or even encode physical principles in the deep learning architecture. And that's a reason for us in the research group of mine. So roughly there are three types of work that deals with modeling turbulence of fluids in a union set of mathematicians, engineers, computer scientists, and even climate science physicists. And I'm actually citing this review paper by Stephen, which I think is fantastic. Review papers gives a broad overview of this field, and we certainly learn a lot from this paper. So here I summarize the kind of deep learning field for fluid dynamics into three categories. One of them is in computer graphics, which is basically the field that tries to design all kinds of animated movies based on principles from physics. So fluid animation basically design faster algorithms to simulate fluids such as rain, snow that you see in CGI movies. So in fluid animation, they emphasize more about the simulation realism, means that as long as it looks good, then we're happy. But they don't care so much about the physical interpretation of the simulation, which is critical for scientific applications such as climate science. Simultaneously, there's a lot of excitement in the community of fluid and turbulence modeling of using deep learning tools as a functional approximator, because we know deep learning are universal functional approximators. So there's this kind of field called data-driven turbulence modeling, data-driven deep learning, which is trying to use deep neural networks as a functional approximator to approximate all kinds of numerical operators in partial differential equations. So obviously, some of the promising results have come out from this line of work, but I would also want to argue that there's no explicit physical constraints in how deep learning was used in this type of fields. So an emerging area of study, which I'm very excited about, is this area called physics-guided deep learning. So this is a type of tools that we develop that's to combine the strengths of deep learning and the domain knowledge from physical sciences. So there's actually a huge amount of literature in physics-guided deep learning or physics-informed deep learning to incorporate various physical constraints or physical laws into deep learning for the application of science and engineering fields. But then there's still several limitations when it comes to fluid dynamics. For example, they often assume there's no external forces, which is not true in climate science, because when we want to model the ocean, there's gravity, which acts as an external force. And then sometimes there's a type of tools called physics-informed deep learning, which is essentially using automatic differentiation in neural networks to solve for partial differential equations. And in this case, you need explicit boundary conditions as input. And then when we do forward simulation or when we do forecasting into the future of a fluid, we actually do not have access to the explicit boundary condition of the fluids. So there's also other works, which is the predecessors of our work, that only focus on spatial modeling. So they solve for partial differential equation or simulate an interpolation region, where ours focus on temporal modeling and temporal dynamics and focus on extrapolation region to forecast the evolution of fluid field. So the first work I want to show you is a paper that we developed together with scientists in Lawrence Berkeley National Lab as to build surrogate models that can speed up the turbulence simulation. So this is an example that actually Stephen mentioned called Rayleigh-Bernard convection. So this happened when the cold fluid on the top interacted with the warm fluid in the bottom. So this creates complex patterns as shown in this video, and it resembles the dynamics of El Nino. Right? So that's precisely why we want to study this type of fluids. So this is a work done by my PhD students and our collaborators at Lawrence Berkeley National Lab. So this video you saw, it only shows for like a couple of seconds, but it took several months to simulate at this kind of resolution, right? So computing complex turbulence at a high resolution is a fundamental challenge in climate science. So our goal here is to develop a deep learning surrogate model that can bypass expensive numerical simulations and directly give us the velocity field of the turbulence. So when we're looking at turbulence modeling, we have to basically look at what has been done in the field of computational fluid dynamics, right? And we know that turbulence is governed by Navier-Stokes equations, and they describe the motion of viscous fluid. So Stephen actually alluded to this method called Reynolds averaging. So this method essentially takes the velocity field W over space X and time T and decomposes into two components. And one is W bar. It is computed as the temporal averaging of the velocity field. And then the residual term W prime. And here you can see the operator G of S is a temporal filter that computes the average velocity flow over time. Naturally, there is a different type of technique that looks at the spatial averaging. So large eddy simulation, or LES, decomposes the velocity field W into two components, the spatial average field W bar and the residual term W prime. And then the operator here, G of X, given Cassie, is known as the spatial filter. So traditionally, people would design manually design spatial filters and temporal filters to compute the average velocity field. And this is just an approximate way to quickly, simulate the velocity field. And also this kind of technique represents the multi-scale decomposition of the velocity field. And this is a figure known as the Kolmogorov energy spectra, right? So we know that large eddies have a smaller wave number, and they basically corresponding to larger scale phenomenon in the turbulence. And then small waves has higher energy and higher wave number or high frequency. So this on the other side of spectra. So when we apply Rens or LES coupling or Rens or LES to turbulence field, we essentially decompose the velocity field according to their scales. Naturally, there's also this combination of two methods, which is called Rens-ES coupling. So it first is decomposed, uses a temporal filter to filter out the temporal component, and then takes the residual and feed that into spatial filter and compute the spatial averaged field. So these two things combined together is called Rens-ES coupling. Any questions? Okay. So before, right, the field of CFD had been, designing all kinds of filters, more commonly Gaussian filters, to compute the spatial or temporal averaged field. Well, our idea is that instead of manually designing this type of filters, why can't we just use a deep neural network to learn the filters? And in this way, the filters are much more flexible, right? And we're not constraining the filters in specific fashion. And perhaps we can also learn interesting average behavior that we did not know before. And that's what we did in this paper. So we have the spatial filter G01, which is a mathematical operator. And then we have the temporal filter G2, which is another mathematical operator operating on the velocity field W. So we can simply replace these two filters as convolutional neural networks, because these two mathematical operators are essentially acting as convolution. So that leads to our hybrid model, which we call Turbulent-Flow Net or TFNet. So in this TFNet, we took the idea of multi-scale spectral decomposition of fluid. So given the velocity field W, so you need to look at the picture from the bottom up. So given the velocity field W, we first feed it into the spatial filter, which is nothing but a convolutional neural network, and that compute the spatially averaged field. And then we take the residual and feed that into a temporal filter. So that compute the temporal average velocity field. And then we model the residual separately. So for each of the components, we will use a UNet, which is a state-of-art method for spatial temporal prediction. And this UNet contains an encoder network, which is nothing but a multi-layered convolutional neural network. And then all the three components share the same decoder D. And then for each of the component, which is it's a UNet, which is shown on the right-hand side of this picture. And this UNet has multi-layer convolutional structure with residual connections to alleviate the gradient vanishing problem. Any questions? Okay. So basically the idea is that we can use multi-scale spectral decomposition, but learn how the spatial and temporal average was achieved without manually designing the filter parameters.
I guess I do have a question. Did you get significantly different performance if you did the temporal filter first?
Oh, that's a great question, actually. Because here we are not differentiating between these two layers, because they're just two convolutional neural networks, even though I call it spatial or temporal filter, but they're essentially the same in deep neural network architecture. Yeah, hope that answered your question. Thank you. Okay, so we applied this technique to a data set generated by a numerical simulator. It's a two-dimensional Raynaud-Bernard convection, and it's in the turbulent regime. So our experimental setup is that we're given the past 12 frames of the turbulence and trying to forecast into the future for 60 times ahead. And then each sequence has 90 steps in the frames. So we reported our number averaged over 3 runs. So this is a two-dimensional Raynaud-Bernard convection, which means, you can think about it when you get up in the morning and then you pour milk into the coffee, and you will see that two-dimensional turbulence on the surface of the coffee cup. So that's a two-dimensional Rene-Bernard convection. Okay, so here is the prediction performance. The left plot shows the forecasting root mean square error versus the forecasting horizon. So we compared with a large number of baselines. So TFNet in blue is our method, and then UNet in GANs, ResNet convolutional LSTMs. So these models are purely data-driven models developed in computer vision or machine learning community for forecasting natural videos. So they do not encode any physical principles or physical laws in the architecture design. SLT or sea surface temperature is a recently published method that actually has similar flavor as our technique. So it basically approximates the Green's function with trainable operators. But we know that Green's function only exists for linear differential equation and does not apply to highly nonlinear Navier-Stokes equations. And then deep hidden physics-based model is this type of technique called physics-informed deep learning that uses auto-differentiation to solve for partial differential solutions that explicitly require the boundary condition as inputs, which are not available in this experimental setup. So we can see that when we look at the forecasting RMSE versus prediction step, our method is relatively robust compared to other baselines. And generally the error grows as we forecast into the future because of the chaotic nature of the turbulence. And then on the right plot, we show the average time per frame for different methods. And Lattice-Boltzmann method is the original numerical method that generates this flow. So we can cut the runtime per frame by half. And this is only for two-dimensional turbulence. We also experimented with three-dimensional turbulence at various density, where we observe 3 orders of magnitude faster than the numerical method. So we can see that TFNet consistently outperforms on the forecasting prediction error, and it shows the potential of using deep neural networks as a surrogate model to speed up turbulence simulation. But these actually are not the most important things I want to show you, because the original idea of our design is to combine physical intuitions with deep learning. So what really matters is whether the predictions are physically meaningful. And here is the metrics that we evaluated, because we're looking at divergence-free turbulence. So the closer to zero the turbulence gets, the better, right? So the left plot shows the mean divergence across different forecasting horizons. And then the black solid line is the ground truth, which is the velocity field generated by the numerical method, Lattice-Boltzmann method. We can see that the predictions of our method in blue, TFNet, has the closest divergence compared to all the other baselines. Another important factor I want to mention is that there is actually a simple way to enforce divergence-free, which is essentially adding the divergence as a regularizer to the loss function. So it's a typical way of incorporating physical constraints. But what we observe is that when we add the divergence-free regularizer to the loss function, the predicted velocity field becomes very blurry. So it shows this kind of interesting trade-off between like adding physical constraints and the prediction performance of deep neural networks, because we cannot, because of the degrees of freedom in the deep learning model, we actually cannot explicitly enforce what we wanted to achieve, which is divergence-free and sharp predictions in terms of video. So the right plot is the energy spectrum decay, the Kolmogorov scale plot of different methods. And the solid black line is the ground truth. So the closer it gets, the better. And the 2 dashed lines in blue and gray are the theoretically calculated Kolmogorov scale decay. So we were told that this picture is the golden picture in CFD. So if we get closer to this black line, the better. And we can see that for large wave numbers, which correspond to small scale dynamics, 2 variations of our model, TFNet and constrained TFNet, has the closest energy spectrum to the solid black line, as in ground truth, whereas purely data-driven models such as UNet and ResNet fail to achieve small-scale dynamics. Okay, so then I want to show you the prediction results from our model. As I mentioned, this two-dimensional Rene-Bernard convection resembles the turbulence you observe when you get up and pour milk into coffee. So what you should expect is this revolving pattern in a two-dimensional surface constituting like circular patterns of two types of fluids. So this is a target, right? And then you can see that the ground truth turbulence has like small scale dynamics and they're rotating each other in a circular pattern. And then this is a prediction of our model. You can see that it closely resembles the ground truth dynamics, even capturing the small scale patterns. But let's look at purely data-driven deep learning approaches, such as ResNet. So this method learns the circular patterns of the turbulence, but it lost a lot of the small scale dynamics. So what you see is that it becomes very blurry and smoothed out velocity field. Similarly for GANs, right, or generative adversarial network, it's an unsupervised method for learning high dimensional distributions. And again, it does not capture the correct type of circular pattern and it lost all the small scale dynamics. So this shows, it is very important to consider a hybrid method that interpolate between traditional CFD techniques and modern deep learning to be able to generate reasonable predictions that are meaningful to scientific applications. Any questions? Okay, great. Feel free to interrupt me at any time. All right, so I have showed you, okay, I think there's a there's one final slide I want to show you is that what this type of model has learned, right? Because we want to open the black box of deep learning tools and try to understand what it has learned. Because our model was designed based on the intuition that fluid can be separated according to the spectral scales. So we hope that this model can help us separate different scales in the turbulence automatically. So what we did in this experiment is that once the model is trained, we manually set all the weights to be 0. So we enforce all the components except for one to generate 0 predictions. So that allows us to examine the predictions of individual components in our model. So the target is a ground truth, right? TFNet combines all the 3 different components. And then the temporal, spatial, and fluctuation are the predictions of individual components when the others are zeroed out. So let me show you the predictions. So you can see that the temporal filter doesn't change much, right? But if you watch the fluctuation term in the bottom, it starts to show this like high frequency fluctuations in the turbulence. And note that we did not encode any equations in this model or any manually separation in terms of spatial and temporal or fluctuation. The model just learns to separate these scales automatically, right? So let me play the video again. So the spatial corresponding slightly larger scale and fluctuation is the highest frequency of the turbulence. All right. So far I have showed you the promise of deep learning when applied to fluid dynamics, and it can act as a surrogate model to significantly speed up turbulence simulation and hopefully be integrated into huge climate models to speed up a lot of the predictions that we want. But one of the major bottlenecks for this line of work is generalization, right? Because we can train our model on a specific turbulence with a given initial and boundary conditions. But then a lot of times when we apply the trained model to a completely different turbulence with different initial and boundary conditions, the model will fail. And this is a problem known as distribution shift in deep learning. And that's what we set out to change, right? And this new paper that we worked on like early this year is based on the idea of symmetry. So we think symmetry is one solution that can help us design deep learning models that are not only faster than numerical methods, but can also generalize to a wide range of fluid dynamics. And this work was led by my PhD student and my wonderful postdoc, Robin Waters, who is on the job market this year. Okay, so what we want is that deep learning can speed up turbulence, right? But its inability to generalize to different distributional shifts limits its application to real world. So when we look at fluid or physical phenomena, an important concept is conservation laws. And then the key insights of this work is that we can leverage conservation laws to improve generalization of deep learning models. Because we think when we move from training to testing, when we're dealing with a slightly different turbulence of different initial and boundary conditions, even though the dynamics have changed, the laws of physics do not change. So if we can encode the laws of physics in deep learning architectures, then this model will be able to generalize automatically. So notice law gives the correspondence between symmetry and conservation laws. So for every symmetry, there is a conservation law. For example, translational symmetry corresponds to conservation of momentum. Time invariant symmetry corresponds to conservation of energy. So we use symmetry as an inductive bias to basically improve the generalization of our deep learning models, to encode conservation laws into architecture design, and hopefully build more trustworthy tools for domain scientists. Before we get into how we design symmetry-aware neural networks, right, let's just refresh on some of the group theory we learned in undergrads. Basically, a group is a set G with a composition map, right? So G, cross product G mapped to self, and then an identity is an element in this group. For every element in this group, there is an inverse map, G inverse. A familiar group is SO2 rotation group in 2 dimensions. And then we know when we rotate clockwise 60 degrees, there is always an inverse operation that rotates the same object counterclockwise by 60 degrees. So what we mean by symmetry in the context of group equivariance is that there is actually two types of symmetries that we're talking about. One is called invariance. The other one is called equivariance. So given a function f and a group G, which is a set of transformations, we say that this function is G invariant with respect to group G when we apply this transformation to the input of the function G of x, the output stays the same. So f of G of x equals to f of x. And if the function satisfies this kind of condition, we say that function is G invariant. More generally, when we have a group that applies to the input of the data, the input of the function, G of x, when it can automatically apply to the output of this function, in other words, f of G of x equals to G of fx. And if the function satisfies this kind of condition, we say that the function is equivariant. An example for that is, let's say we are looking at a function which is a velocity field of a 2-dimensional space, and this function basically stretches the velocity vector by 2. So f of x of v is x and 2v. And then let's consider the 2-dimensional rotation group, which can be represented as a 2x2 rotational matrix. It's an orthogonal matrix that rotates the velocity field. So if a function is equivariant, which is essentially a more general version of invariant, right? Because when we set the group to be identity, then this equivariant function naturally becomes invariant. So when we're looking at a velocity field on the top left corner, when we first stretch the velocity field by applying this functional transformation and then rotate it by 45 degrees, it is the same thing as we first rotate the velocity field by 45 degrees and then apply the transformation of scaling, then they're essentially the same. So in this case, we say that the function is equivariant. So we wanted to design functional approximators that are intrinsically invariant. So we want a neural network essentially to learn a function that is G invariant. right? We know a function is universal functional approximators. So given a function, we can stack a bunch of layers together. And as long as we can show that each map between the layers are equivariant, then the entire network is equivariant. Even adding skip connections does not change its equivariance. But the question is, how do we design this kind of equivariant networks? The idea was actually not new. So if you are familiar with convolutional neural networks, right, we know convolutional neural networks are translation invariant, where the way it achieves translation invariant is through weight sharing. So if you're looking at the symmetry group of translation, where we move from one pixel to the top left corner to the another position in the right bottom corner, then we're assuming that the weights in the orange blocks across diagonally are all shared. But then the weights inside of the orange blocks are completely freely trainable. So in this way, we can basically encode symmetry directly through the design of the neural network without using regularizers in the loss function. Right? So, and then in general, this is a recipe of how we can design equivariant networks for arbitrary groups. Essentially, we need the kernel in the convolutional neural network to satisfy this property called in group invariance under conjugation, where we apply the group transformation on the left and right hand side of the kernel. As long as it doesn't change, then this convolutional neural network will be equivariant to a particular group. So the real tricky business is, how do we figure out the representation row of G, and row in and row out, which is the matrix representation of the corresponding groups. So basically, I can skip this because of time limit, right? But let me show you an example of how we can achieve scaling symmetry for turbulence. Because the coffee example I mentioned is a small scale turbulence. And when we look at climate science, the turbulence in the ocean, it's a much larger scale turbulence. And we know that convolutional neural networks are only translational invariant. So in order to make it scaling symmetry, we have to design something different. So we must actually translate and scale the kernel across the input. And that's what we did in this paper, where we show 7 different symmetries and how we can design the corresponding equivariant neural networks. So for scaling, for instance, we have the velocity field from the ocean, and then we can basically upscale the velocity field by different factors. And then we assume the weights in different kernels across scales are all shared, but the weights within the kernels are freely trainable. And in the end, we aggregate extracted features across the scales, and in that way, we can achieve scale equivariance. So mathematically, it just means we need to design this type of kernel, tau of k, where tau is a scaling operator. And this scaling operator actually can be directly borrowed from the symmetry of differential equations. And we know that Navier-Stokes equations satisfy this kind of lambda, like half space quadratic time scaling law. So this can be directly encoded into how we design convolutional architectures for scaling symmetry. So this is, I promise this is the final slide of this presentation before I conclude. So we actually applied this method to forecasting the ocean current generated by from the NOAA website. And then we're looking at a different forecasting root mean square error versus the upscaling factor. So this is trying to test whether the model is robust against a different kind of distribution shift. So we train our model on a particular scales of turbulence and test our model at a completely different type of scales of turbulence. So what we can see is when we upscale the test set by different factor 1 over lambda, and the non-equivariant model, the ResNet, will have exploding error because of distribution shift. Whereas the symmetry aware equivariant networks, because it can detect the changes from training to testing and apply the transformation from input to the output. So the prediction of our model is quite robust. And this phenomenon not only happened in the pixel space for root mean square error, but also in terms of physical metrics such as energy spectrum error, and is quite robust against group transformations. Right, to conclude, I talked about some ideas of physics-guided deep learning, where we want to integrate first principle ideas, laws into deep neural networks. I talked about TFNet, Turbulent-Flow Net, which is a hybrid model that combines CFD techniques with deep learning to accelerate turbulence simulation. I talked about Equivariant Networks, which is type of symmetry-aware neural networks that directly encode conservation laws in the design of the architecture. And we showed that this model can help us generalize to very different dynamic of phenomena. In terms of future work, we're actually very interested in the flow control and optimization problem, which is something orthogonal to what we have done so far, which is more about dynamics modeling. And with that, I want to thank everybody for supporting our work. And this is my website. You can find the data and the source code available on my website, or follow me on Twitter, where I sometimes publish news from our group. And here are the funding agencies that supported our work. Thank you very much.
Questions? Is there anything from the audience online?
Fantastic work, Rose.
Thank you.
Can you go back a couple slides to one of your results? So what does that dip upward at 2?
So actually, because I think we have some hypothesis of why it happens, because when we actually, because scaling is actually a continuous group, right? And then we actually have to like truncate in terms of different order when we implement upsampling operator. So there's, even though the model by design, it should be perfectly equivariant, but in implementation, it is not perfectly equivariant. And because of that, it will affect the prediction error. Yeah, but this is just a hypothesis. Yeah, thank you. That's a wonderful question.
Great talk. So in the first part, when you use a unit to learn the filters, have you looked at these filters to see actually what they are and what are the kind of filters that you are learning?
Yeah, so we just basically did this ablation study that I showed you, right, to see whether, you know, so this like what is these filters are doing, essentially, like separating the scales of velocity. But we haven't looked at the actual numbers in the filter because there's just too many of parameters in the neural network weights. Great question.
I'll ask while we figure out what Duncan wants to.
Yeah, can you hear me?
Yeah.
Fantastic. Thanks for the really nice talk, Rose. Actually, the question was relating to this slide or this work on Turbulent-Flow Net. Are there opportunities, given this decomposition, to learn some of these smaller spatial filters with limited observations? So if you could learn the larger scale temporal filter from, and I'm thinking here in, you know, general climate models or general circulation models, and then you're able to use a few higher resolution simulations to learn the filters. Is that something that you could use with this approach?
Yeah, I mean, that's a really insightful comment. So like, I feel we definitely could, in principle, just like to interpolating what actually are designed versus what is actually learned. So because these components are actually they're sort of independent from each other given a decoder. So we can certainly do that. Yeah.
That's really interesting. Thanks.
Mm-hmm. Thank you.
Yeah, thanks, Rose. Actually, it was almost the same question as Duncan. Did you actually try to do that on, you know, output of real models? So you showed us the forecasting of observation. You also showed, you know, the beautiful maps of ocean simulations that are very turbulent. So maybe pretty cool to actually try this kind of filtering approach on the output of climate models.
Yeah, I would love to. Like, I mean, if you have good references, like what data set or what experiments you run, I'd love to hear your insight.
So we have a climate model developer right here.
That's fantastic.
So is that fantastic. That?
Thank you for the pointers.
Thank you very much. Yeah.
So, Rose, I mean, this is just truly amazing stuff.
the symmetries is the way I'm understanding it is you've kind of built symmetries into your networks. And it reminds me of the way that we do numerical methods. We always try to look for symmetries in the numerical methods as well, in the way we discretize. But we also take advantage of, from a physics point of view, we are often biased also. So we have state-dependent discretizations which are not symmetric. And I was wondering if your systems can handle or can take advantage of that aspect, that we do have state-dependent, we know that we want to bias things, not be symmetric sometimes.
Oh, I see. That's like really like an interesting question, because we're actually studying right now. Is that how do we kind of deal with partial symmetry or like broken symmetry in some ways? We actually, we just had a paper accepted in Europe this year about automatically discovering symmetry. So because the limitation of the equivariant networks of the entire literature is that we assume, one, we have perfect symmetry, which is not possible in real world. Two, we know what symmetry groups that we're dealing with, and that's from a prior knowledge, but sometimes they may not be available in real world life. So this new paper, I can send you the links afterwards, is that we actually can just like similarly how to scientists discover new phenomena from data, we can design deep neural networks that can discover the right kind of symmetry groups from data. So in some ways, it relaxes the assumption of symmetry groups that we impose on the neural network, right? And can also handle certain situations where the symmetry group is not perfect.
So Keaton Burns is asking, it looks like you compared the TF-net to several other ML closures, but have you had a chance to compare it to classical closures like Smagorinsky scheme or hyperviscosity?
Oh, we haven't, but yeah, I mean, I would love to if you have the more details of the benchmarks or the baselines, because we compare, I mean, the comparison in our case was to show that adding physics to purely data-driven deep learning helps, right? And I'm not sure, actually, I'm not familiar with the technique that I mentioned. If it's like numerical method, then you're probably similar to like lattice-Boltzmann method that we showed that generates this kind of flow. But if you can send me more details, I would love to compare.
Thank you very much.
Thank you. Thank you, everyone.